This section we're going to look at application and models of exponential growth. There's actually a lot of formulas that are associated with this section, but they really all come down to this formula that we have right here. Whether it's exponential growth or exponential decay or compound interest or any of other problems that you're going to be doing in this section, they all are really essentially the same formula. This P of t represents population at time t. P of 0 is population at time 0, or your initial condition. If you're looking at compound interest when you have money, this P of 0 represents the starting money that you have or your principal. This E, remember, is Euler's constant. It's a number like pi, it doesn't change. It's programmed into your calculator. And that is, to find that, you use second ln button on your calculator to use E. K represents your growth constant. Now, if your growth constant is greater than 0, you're going to have growth. In other words, your exponential function is going to look something like this going up. If your k is negative, where it's less than 0, you're going to have decay, or you're going to have things getting less, and your curve is going to look something like this. And then t here represents time. So let's do an example. Let's say you have a country with 10 million and their growth rate is 1.5% per year. And you want to know, what is the population of the country going to be in 15 years? So we use our population model where we have P of t is equal to P of 0 sub 0 e to the kt. And you're basically just going to fill in the blanks. P of t is 15. That's equal to 10 million. E, the growth rate as a decimal, is 0.015. And we're going to do it for 15 years. So it's really just a calculator problem at that point. I'm going to do 10, and then I'm going to do second, and then ln down here. And that's going to give me this E right here. I don't know if you all can see that, right? So it doesn't matter if you have a scientific calculator or a graphic calculator. Both of them will do exactly the same thing if you do second ln. Then I'm going to do 0.0515 times 15, and I'm going to get 12.5 million. And that's what most of these problems are going to be. They're just going to be plug and chug type things. But let's say we want to ask how many years to 20 million. So we use the same formula again here. I'm going to put 20 here as in my ending population. My initial population, I'll use the same conditions that I have here, 10 million. E to the 0.015, and then t here is what I'm going to solve for. This is where we're going to have to use the properties that we learned in the previous sections when we're solving exponential and logarithmic equations. First thing we want to do is get rid of this 10 here. So I'm going to divide by 10 on both sides, And I'm going to get 2 is equal to E to 0.015t. Now, whenever your variable is in your exponent, you want to change the form to solve for it. And I can do that two ways. I can change it into log base e of 2 is equal to 0.01015t, which is really just the natural log of 2, because log base e of 2, divided by 0.015, and that's going to give me t. Or you can take the log of both sides. We can do the natural log of 2 is equal to the natural log of e 0.015t. And then we use our power property to bring this down front. So we have a natural log of 2 is equal to 0.015t, and natural log of e. Now the natural log of e is equal to 1, and we're at the same place. So whatever method you're most comfortable with is just fine. So now I'm going to do the natural log of 2, close parenthesis, divide by 0.015, and that's going to give me 46.2 years. Okay? That's essentially what all of these problems are going to boil down to. They're going to ask you, what's the population going to be, or how much are we going to have after a certain number of years, or how long is it going to take to get to a certain point. Now, some of the questions are about doubling. And this is actually pretty simple. You can pick any number. Let's say that your growth rate is 5%, and you want to ask how long to double. Now, there's a formula in the book that you can use, but honestly, just use this equation. That's the only one you really need for any of this. Make this 2 is equal to 1 e 0.05t. Whatever you're starting with, you're going to get twice as much in the end. Now, it really doesn't matter what p of sub 0 starts with. So let's say that you wanted 15. Well, that will double to 30. But then your very first step you would do in solving this equation, just like we did up here, is you're going to divide by 15 first, and you're going to get 2 is equal to 1 e to the 0.05t. So when you're doubling, just set it up so that you have 2 here, 1 here, your rate and your time, and then you solve it just like we did up here. This will be the natural log of 2 is equal to 0.05t, where t is equal to the natural log of 2 divided by 0.05. We're going to get t is equal to 13.8 years, months, whatever. We didn't really specify an amount of time. So in a very simplistic sense, this is how all of these problems go. There's a lot of videos that are associated with this section. I encourage you to check those out. They are going to be right here. Remember that you have your multimedia library right here. And then in your multimedia library, we can select the chapter. We can select the section that we're looking at, and you click select all, and you're going to click find now. All of these videos are very good. They go through all the specific examples that you're going to be responsible for in this section. Now, I could remake all these videos, but there's really no point. All of these are actually really good. Okay, and it goes through all of the examples in the book. These guided visualizations are also pretty neat as well. It allows you to look at an actual graph of an exponential function. Here in this example, we have initial condition of 5. We have a growth rate of 0.12 or 12%, and we can see what that curve actually looks like. Now I can change my initial condition by using the slider here, and we can look at how that graph is actually changed. It's literally off the scale. Okay. We can change our growth factor. We can see what happens when it becomes negative. We're going to get our exponential decay. But when it becomes positive, we have our exponential growth. See, let's do our y max here. There we go. So now I can increase my initial condition. Y max right here. There we go. Now we're talking. So now I can change this part here, and that's still, you can see it increases quite rapidly. All right, that's going to end part one. I'll come back with a couple of more examples.